So this process that we laid out is the same for integrals involving the terms something similar to the square root of a squared minus x squared, or the square root of x squared minus a squared. So just notice the order of the constant and the function. But in those cases, you'll use different trig functions for your substitution. So in general, this is what you want to keep in mind. So if you have a form that's the square root of a constant minus function, then you're going to use a sine theta for your substitution. If it's a function minus a constant, you're going to use secant as your substitution. And then if it's a sum of a constant and a function, you would use tangent as your substitution. And the reason we use different trig functions is because ultimately the choice of the trig function leads to a different set of sides initially that are set up on the right triangle. So for instance, if I'm using the substitution u equals a sine theta, then what that could be interpreted as is sine theta equals u divided by a. Okay, then if I have a right triangle and some observed angle theta, then sine, just based off of SOHCAHTOA, so sine is the opposite side over the hypotenuse. So the opposite side is u, and the hypotenuse becomes a in that case. Now, what becomes this remaining side? Well, using the Pythagorean identity, we know that the sum of the two shorter legs squared is equal to the hypotenuse squared. So if I want to figure out this missing value, I would subtract u squared from each side. So the missing value is a squared minus u squared. And then when I take the square root, that remaining side is the square root of a squared minus u squared, which is the order of the constant minus the function, which is what we stated we would use sine for. Secant, you just set up two other sides of the triangle, and it results in the function minus the constant. So you have three different pieces that you can use to substitute with. Now, another question I often get here is why sine, secant, and tangent, and not sine, cosine, and tangent? Well, in trig, we kind of get used to the fact that the three basic trig functions are sine, cosine, and tangent. And then you have the other ones, secant, cosecant, and cotangent. But really the truth is, it's actually sine, secant, and tangent that are your base trig functions, and the other three are, well, your other trig functions. They're called cofunctions because they're complementary, so they're off by 90 degrees to another trig function. So cosine is the same thing as sine. It's just off by 90 degrees. So sine and cosine are effectively the same function. So there's no reason to use sine and cosine separately here when sine and secant give you two different functions. So you have sine, secant, tangent, and then the respective cofunctions, cosine, cosecant, and cotangent. So just to clear that up. Now, also, I'm using a u here, and it's pretty common in u substitution to use the letter u for substituting, but we're generally going to substitute with the variable x. It's just, when we have a function of the form the square root of x squared minus 4, then my u is equal to x, and it would substitute with x equals 2 sine theta. Okay, let's look at an example. Now, this example I have chosen on purpose. We've seen it before. And if you bear with me for just a second, I'm going to scroll up to where we saw it. It is this example right here. So the integral of 1 over the square root of 4 minus x squared dx. And we've already seen that this is equal to the arc sine of x over 2. But here we're actually going to see why that's the case. So let's go through this process and see how that works. Okay, so I have something of the form which is a constant minus a function squared. So my substitution would be this function, well, the square root of that function equals the square root of the constant sine theta. So that's the big important step. Once you get there, the rest of it can really just fall into place. You decide on that substitution. Now, later on, you're also going to need substituting for dx. So go ahead and take the derivative of this equation. So the derivative with respect to x would be 2, the derivative of sine is cosine, and then d theta. And at this point, you really could substitute in for x, the 2 sine theta, and dx, this, and work it through. But I really generally prefer using the right triangle setup to help with the substitution. It's up to you, though. So if we're saying that x is 2 sine theta, then also another way of looking at that is sine theta equals x over 2. So if I call this angle theta, then the opposite side from that would be x, and the hypotenuse would be 2. Now if I solve for this remaining side, which is a good idea because if you've made a mistake in choosing your substitution, it might be a few steps along the way before you realize that there's a problem and it's not, your integral's not going to work. But if you solve for this triangle piece right away and it doesn't work, that tells you very early on that you've made the wrong substitution. So I tend to just go ahead and solve for this and, just kind of off to the side. Maybe I'll even use a different color because it's, so let's see, that side is a shorter length, so that side squared plus x squared equals 2 squared. So that missing side is 2 squared, which is 4 minus x squared. So this missing side here is, of course, what we expect it to be, 4 minus x squared. So it matches the part that's inside my integral, which is great. Now, here's the next thing. So I have something to substitute dx with. I need something to substitute this radical with. So just based off of the different sides of my triangle, I could come up with a couple of things, I think. So one is I could use cosine. So the cosine of this angle theta is going to be the adjacent side over the hypotenuse, which would be the square root of 4 minus x squared over 2. And that's not exactly the square root here, so I'll just multiply everything by 2 and make it exactly that. Another thing I could do is I could actually use secant because this square root's in the denominator, and I could say, for instance, like the secant of theta is 2 over the square root of 4 minus x squared, and because it's not 2 over that, it's just 1 over, I could divide by a half. Well, divide the 2 over and make it a half, that is. And then I could substitute with this. So there's multiple ways of approaching the substitution part. But it's up to you how you choose to go about it. You will get to the same simplified form no matter which way you go. So keep that in mind. All right, so I am directly substituting for dx, and dx is 2 cosine theta d theta, and then I'm directly substituting for the square root with 2 cosine theta. Okay, if you'll notice here, the 2 cosine theta appears in the numerator and denominator, so that just cancels out, and I'm left with the integral of just d theta, which is just theta plus c. And the only thing left to do is to change that back into a trig function. I'm going to get back to a function of x, that is. So to do that, I go back to my triangle and figure out how to make that work. But in this case, I'm looking for something for theta. I need to use an arctrig function. So I could focus on this, for instance, because if sine theta is x over 2, then I could conclude that the arcsine of theta, the arcsine of x over 2 is equal to theta, because I would take the arcsine of both sides. So that would be arcsine x over 2 plus c, which is the same response that we got previously. So that's great. That gives us a way of understanding the process that we were doing before, and this is where it all comes from. Now, it is actually possible to get a different response. Like, for instance, if I had chosen to solve this equation for theta, I absolutely can. I would take the arc cosine of both sides, and I would end up with theta equals the arc cosine of the square root of 4 minus x squared all over 2. And that's a perfectly valid thing to write in for theta as well. So you might get something that's very different from a form that's in like the answer in the homework or in the back of a worksheet, for instance, but it still could be completely valid. So you might, if you are certain that you've got a question correct, you might want to just check with the instructor before you assume that you've done something improper. Okay, in this next example, I have the integral of x cubed times the square root of 1 minus x squared dx. So the identifying thing here is often this square root. So you have a square root of something that has two perfect squares underneath it, either added, subtracted, and that's your general tell. Now, there are some nuances to that, but for now, that's the thing you're mostly looking for. All right, now underneath that square root, I have two things that are subtracted, and it's of the form of a constant minus a function. So when it's constant minus a function, we're using the transformation for sine. So that's going to be x equals, the square root of 1 is just 1, so technically 1 times sine theta. All right, so that's just our first step. Choose the substitution. Now, when we choose the substitution, there is some things that happen based off of that. Number one, we are going to need something to substitute for dx. That's important. So if we substitute in for dx, this would be the derivative of sine theta. So we would substitute in cosine theta because the derivative of sine is cosine. Now, at this point, you could substitute sine in for x cubed and x squared and just go straight from there and work the problem out. And that's often how the textbook does it and many of the online help videos. But I really think that it's very helpful to, at this point, draw out the triangle that you're going to need because you're eventually going to use it anyway. Set up an observed angle. Then based off of what you chose for sine, since we know that sine theta is the based off of SOHCAHTOA. So SOHCAHTOA means that sine is the opposite side over the hypotenuse. And since we're saying that sine is x, we can say that's x over 1. So the opposite side from our angle and the hypotenuse would be x and 1. And then just to verify this remaining side, just make sure it looks like the square root. So if I take, say, the square of the known side plus the square of the missing side, that's supposed to equal 1. So the missing side squared would be 1 minus x squared. And if I took the square root, that would match up exactly with what I have inside the integral. All right, so that brings me back to the integral. And At this point, I can now start substituting some things in. So to substitute in for x cubed, I know that x is sine theta, so I can also say that uh, sine cubed theta is x cubed. So I can just make that sine cubed theta. Then the square root. All right, so I don't technically have anything to substitute right away, but if I look at my triangle, based off of this angle, theta, this is my adjacent side and this is my hypotenuse. So if I were to take cosine of this angle measure, then the adjacent side over the hypotenuse would be that square root divided by 1, which is nice because I don't even have to take care of a constant. I can substitute that directly for cosine theta. Now, of course, if I would have substituted sine squared in for x squared and reduced the square root, it would end up in the same place. It's just a little more efficient using the triangle. And then, of course, the x has to be transformed using cosine theta d theta. So that gets us to this point. Now, the next thing is, well, actually, let me go ahead and label this. The second step in this process is to transform your integral. And you want to make sure you're in terms of theta. Okay. Now, the third step is to actually integrate. So we want to simplify this as much as possible to get us into a form where we can integrate. So I'll just combine these two factors of cosine, and we're now in the third step of this process and integrating. Okay, to integrate, we've got these powers of sine and cosine. Sine has an odd power, so I'll preserve one of those factors and then change the remaining sine squared into 1 minus cosine squared. And multiply n. So this would be cosine squared minus cosine to the fourth, well, sorry, of theta, d theta. And at this point, I can now use u substitution. So when doing u substitution, I can say u is cosine theta, and du would be, the derivative of cosine is negative, so be careful there. So this would be negative sine theta d theta. Now, I have a sine theta and d theta. I don't have a negative in there, so I'm just going to put a negative outside of the integral to take care of that. So I have the negative integral of u squared minus u to the fourth du, or more simply, u to the fourth minus u squared du. All right, now this will integrate pretty easily because it's just the power rule at this point. So that's going to be u to the fifth over 5 minus u to the third over 3 plus c. And then we need to go back to the original variable here. And it's going to be a little bit tricky here because we used a substitution to go from x into theta and then again to go from theta into u. So we kind of have to back up one at a time. All right, so first off, the first thing I did was transform u into cosine theta. So I'm going to take u and go back to that. So this would be, say, 1/5 cosine to the fifth theta minus 1/3 cosine to the third theta plus c. But I'm not finished yet because then the next thing is cosine theta needs to be transformed back into x. But nicely, I also have this transformation right here, which will bring me back into x. So I can now say this is 1/5, and then cosine theta is this square root. So I'm going to write 1 minus x squared to the 1/2 power. But since that's also getting raised to the fifth, that's going to be to the 5/2 power. Minus 1/3, whoops, not cosine anymore. Sorry about that. 1/3, 1 minus x squared to the 3/2 power, and then plus c. And then that's our final step here, which is always step 4, which is to rewrite back in terms of the original variable. And then we're all done. Often it's the same 4 steps, even though this looks like a very involved process. If you focus on each step independently, it's not that bad. Each step kind of is a little bit, but you know, one thing at a time, and the whole process isn't that bad overall. All right, this next example is a different type of substitution. So if you'll notice, the order of these variables is the function minus the constant. So what that means is u is equal to x and a is equal to 2. We will be using the substitution x equals, so it's u equals a secant theta in this case. And then of course you do need to make sure you know the derivative of secant. That's going to be 2 secant theta tangent theta in this case. Okay, now once we have chosen that substitution, I'm going to go to making a triangle here and saying this is theta. Based off of this relationship right here, I know that secant theta is x over 2. Well, secant theta is the inverse of cosine. So cosine is the adjacent over the hypotenuse, so secant is the hypotenuse over the adjacent side. So when we solve for this remaining side, we would have that side squared is, plus the other shorter side squared is equal to the hypotenuse squared. So the missing side is x squared minus 4. And if we take the square root, we get exactly what we're looking for. So now what we need to decide on is what we're going to use to substitute with for my integral here. Now, I'm going to work with tangent here, because one thing I can see is that the square root side involving, or the side involving the square root and the side involving this constant looks similar to what's in this integral. So I'm going to say that the tangent of theta is the opposite side over the adjacent side, or 2 tan theta is that square root exactly. Okay, now I'm going to do my substituting. Okay, dx is 2 secant theta tangent theta d theta, and the square root we found as 2 tangent theta. And very nicely, we have a tangent that will cancel and a constant that will cancel. So I'm really just left with the integral of secant theta d theta. Now, that is one of our basic rules of integrals. This is one that kind of gets forgotten from time to time, but you might want to look it up. It is the natural log, the absolute value of secant theta plus tangent theta. Okay, looks complex, but you know, it's just a rule. You just memorize it at this point. Then we need to substitute in for secant and tangent. And I've actually already got both of those solved for down here. I can just plug right in. So this would be the natural log, and I'm going to write it as parentheses, and then absolute value. Secant is x over 2. Tangent is the square root of x squared minus 4 over 2. And I need a absolute value, and then close parentheses, and then plus c. Now, why do I use parentheses around the absolute value? Well, it comes down to the homework software. Homework software looks at all functions as the same kind of thing. So absolute value, it sees it as like this. So if the homework sees absolute value of x like this instead of like this. It does not see absolute value as a grouping symbol, it sees it as a function. So if you write natural log of absolute x, it interprets that as lnabs of x, which it doesn't have any idea what you're talking about there. But if you put parentheses around it, it correctly interprets that as the natural log of the absolute value of x. So I put those parentheses there just as a reminder to myself when I go to enter stuff on the homework site to do that properly. All right, so just kind of keep that in mind. All right, and I know this is a bit of a long one, but I want to do lots of examples. I've got one more before we take a break here. And I have this function here, x squared minus 9, or the square root of x squared minus 9 over x. Okay, so first step in the process, we need to decide on a substitution to use. So I'm really just going to focus on the square root to decide this substitution. So I have a function minus the constant, so that's in the form of secant. So it's going to be x equals 3 secant theta. And then the derivative of that, because we need to substitute for dx, that is 3 secant theta tangent theta d theta. Okay, now we need to make our substitutions into the integral. And that's involving setting up this right triangle. Okay, so if this is theta, I know that secant of theta is x over 3. So that's going to be, secant is the inverse of cosine, which is the adjacent over the hypotenuse. So that's going to be the hypotenuse over the adjacent side. And if I just quickly solve for this, I can make sure I've set everything up properly. So 3 squared plus the missing side squared is equal to x squared. Or the missing side squared is x squared minus 9, and that's basically what I want once I take the square root. Okay, great. So now I'm ready to figure out something to substitute with here. Now, I have something to substitute x for, and I can figure out something to substitute the square root for. But here's kind of the cool thing. What I'm looking to do is substitute square root of x squared minus 9 divided by x. I can actually set up this side, which is the opposite side, and this side, which is the hypotenuse. And the opposite and the hypotenuse is based off of sine. But I say sine theta is the opposite side over the hypotenuse, then I've got something that matches exactly both terms all in one, which is going to make my substitution easier. So I go ahead and do those substitutions at this point. Sine theta, and then dx is 3 secant theta tangent theta d theta. Now I need to do some work with setting up this problem so that I can integrate. And right now I have 3 trig functions. 2 of them are related, but one's not. Let's see what we can do here. Let's pull the 3 out. Secant is 1 over cosine. Tangent is sine over cosine. So I could actually rewrite this as 3 tangent squared theta d theta. But I'm not sure that that's entirely integrable on its own. However, I can integrate So tangent is, all right, so back to the Pythagorean identity. Let me come up to the side here. So sine squared plus cosine squared equals 1. If I divide everything through by cosine squared, then I have tangent squared plus 1 equals secant squared. All right, so tangent squared would be then secant squared theta minus 1 d theta. And that's nice because secant squared is actually an integral formula that we know. 1 can be integrated pretty easily. So this would be 3. The integral of, well, let me do it this way. The derivative of tangent is secant squared. So the integral of secant squared is just tangent. The integral of 1 becomes theta. So now I just need to replace back tangent theta and theta itself. So tangent is the opposite over the adjacent, so that's going to be square root of x squared minus 9 over 3. Theta, I can use this relationship here with secant and say that theta is the arcsecant of x over 3. And if I wanted to distribute the 3, it's okay. It wouldn't make any difference, but it does eliminate a fraction, so that's kind of nice. But there we go. There's that final answer.